start. Okay, so we're going to start with this breakout. We did this breakout before. I believe this was the last thing we did yesterday. Let me just format this. Go ahead and get started on this. I'm going to post it in the thread, but go ahead and get started on it if you can see it. There you go. I'm going to put 5 minutes on the clock. You could, of course, refer to your notes from last time if you had a working function, but I want y'all to work through this again. It can be a really useful thing to solve problems that you've already solved before, which might seem obvious or it might seem totally weird, but it's one of the one of my personal most tried and true study practices. There's 5 minutes on the clock. Go ahead and give this a shot. You're going to write this with a while loop. We're going to do review and overview in the whole thing in a minute here, or in a few minutes after we're done with this. As you're working through this, I want you to use the workflow strategies that we talked about, that I went over Thursday. So, make sure you understand your problem statement. I always like to copy it into my editor so I can play around with it, move things on different lines, edit things, make sure I have a clear understanding of the question, the problem statement, make something kind of like a doc string, and then once I'm done with that, I'll use, sorry? Oh, sorry, it's really quiet. Say that again. Oh, it's in Slack. I'm doing stuff in the editor. Yeah, sorry about that. Yep. So yeah, that's why I'm posting it in Slack, because I want you all to copy paste it. You can also find it in the course materials if you click on this where it says slide decks and where I gave a link to while loops. You'll find the question in there. Copy paste it to your editor, Replit, whatever you're using. And then before you start your definition, or if you are already writing your definition, you want to make sure you have a call in place. You want to have a function call in place while you're working. Highly recommended. Okay, I'm going to extend the time a little bit. I don't see any answers yet. Put another couple minutes on the clock. So I apologize. I realize my fans are on me. That's probably a little less noisy. How do you delete a file from REPL? You just play around on those icons on the left. I don't exactly remember which one, but one of them will show you a list of the files that are in that REPL. And then you click on those icons on the left, and when you see that, you just right click on the file that you want to delete, and I think it doesn't say, it doesn't stay long enough. Yeah, I don't know what's with that. For me, when I right click, I get a little menu that stays up that'll have an option to delete. Yeah, I don't know why it's disappearing. Perhaps just refresh the page. Are you using Chrome? Okay, good. If you're on Windows or Linux, do Control-Shift-R on the page, and that'll do a hard refresh of the page. If you're on Mac, it'll be Command-Shift-R, and that'll, yeah, same deal. It'll do a hard refresh. It'll clear the cache and reload the page. Okay, we got an answer in here. I'm gonna give another couple. I'm just gonna do another minute for now and see if we get a few more answers. And this is good. The answer that's submitted is it's in a formatted code cell, which I want you all to do, and it's got 2 tests in there, which is great. Always good to have a couple. If you don't want to do a couple, you can just do one. One is fine. Like, one is, 90% of 99% of the importance of writing a test is captured by writing at least one test. And then the other tests are just to kind of enforce that. So. Oh, I do notice you are using a global variable, though. I'll suggest you rewrite that without a global variable, because that function will actually only work one time. .26 will have all the divisors of 14. I just noticed that. So you'll want to make that accumulator local. I'll touch on global versus local too. Okay, cool. We'll stop it there. Go ahead and just put in what you've got into Slack. Just put it in a formatted code cell. No worries if you didn't finish it. It's totally fine. Get my screen share back up and running. I can find my window. Here it is. Okay. So I'm going to solve this, and I'm going to follow the workflow pattern that I suggested earlier. I've seen, to the person whose solution I was looking at with the global variable for the accumulator, I don't mean to put you on the spot. Definitely this is something that takes some getting used to. You're not the only person I've seen doing this recently. I'll show it, I'll kind of highlight that. So I'm going to go through a solution, and then I'm going to sort of juxtapose my solution with using a local accumulator with a global accumulator. To be clear, using global variables is something that Python allows you to do in the sense that it doesn't throw an error if you do it, but it's something that you should absolutely, under no circumstances, ever do. There are languages that I work in that will throw an error if you try to use a global variable in a function, and I wish Python did that, but I was just about to say if I were to add one thing to Python, but I already said that for type hinting. So I don't know, if I were to add one thing, it would actually probably be the global variable error, and the second thing would be type hinting. Okay. Anyways, if I were to add two things to Python, it'd be those two things. Really. You were wondering why you were getting the same divisors for 14 and 26. Yep, that's exactly the same thing. Because as many times as you run that function, yeah, it'll always just, that function is forever operating on that same list. Okay. So let's look at this. So I'm going to follow, I'm going to do this, like I said, I'm going to follow, so things to watch out for while I'm doing this, workflow. And I will give example of global versus local. And I'm going to start with a while, and I'm going to go to a for loop solution. This problem truly is better solved with a for loop, but we're doing it with a while loop because we're doing while loops. Okay, so workflow. Following good workflow, I always love to have my problem statement in my editor where I can manipulate it and make it read how I like it. Now, part of that is that I think part of that's personal. You don't have to do everything exactly the way I do it. Part of that's a personal thing. Being dyslexic, I read well in a text editor. The colors are nice. The font is monospaced. The font is meant to be, just clear and kind of blocky and easy to read. And I can push things around and format it the way I like. But I think it can be a useful thing. So get your problem statement somewhere at least where you can see it. If you don't have a screen capture tool, like if you're on a Mac, I know I've used a screen capture tool called Snappy App. That can be a really good thing if I'm like going through an algorithm, trying to implement some algorithm from like Wikipedia or just online somewhere. You can take a screenshot of the thing and then move the screenshot around, keep it above what you're doing, and reference it. So I want to have easy reference to my problem statement somehow. Okay, and I'm just kind of randomly formatting this, I guess. I'm not even really thinking about it. Okay, so write a function that computes and returns a list of all the divisors of some positive number. Okay, so we'll say n is some positive number. And I can actually presume it's not just a number, it's an integer, right? So a floating point number is a number, but when we're talking about divisors, or if a number is prime or not, especially with primes, right? There are divisors. I guess you could think about floating point numbers as having divisors in some other way, but that becomes complicated. So we're thinking about integers. So use a while loop to do this, even though we don't need to. And think about how do you determine if a single number is a divisor of another? What is your stopping condition? And then the bonus is to rewrite with a for loop. Okay, cool. So I've got my problem statement all nice and formatted. It's all clarified. Cool. So that's sort of step 0, if you will. Step 1 is really call the function. So I hope that you all remembered to call your function before you define it. And some of you might think, well, it feels really unnatural. Why would I call a function that doesn't exist? It's just gonna break my code. And I forgot to do, yay, okay, good. That's my sanity check. Make sure everything's all plugged in together. Okay, so the reason to call your function before you write it is, remember the ion thing? Input, output, notes, right? These are my notes, kind of, right? These notes are just anything that I need to give me a sense of what it's supposed to do, maybe what I must not do, what I must do, just to obviate what this function does. Just anything else that I need to know. Maybe the function, generally you don't write functions that cause mutations, but I guess there's kind of a special case where you might consider doing that. There are different philosophies about that, but I try to avoid writing functions that cause mutations. If I'm going to write something that causes a mutation, I want it to be a method, because I'm that way. But so maybe in your notes you'd say if it causes a mutation, or if it returns a variable, or if it maybe anything, there's sort of an exception to the rule. Maybe it doesn't return anything. Maybe it calls out to an API and makes a post request or something. So there's various things that it could do that might kind of break from what you would expect, and that's what you put in your notes as well, right? Then inputs and outputs, you're keeping track of what the function takes in, and this relates to why we call it first, and what its output is. So these both relate to why I want you to call the function first. Inputs and outputs. So when you're keeping track of input and output, you're keeping track of the type. If I ever ask you, if we're ever working together and I ever ask you, like, you know, what does blah 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 function take, the kind of answer I'm expecting back is an integer or a list, right? So if I said, what does range take as its argument? You'd say it takes 1, 2, or 3 integers to represent the start, stop, and step, right? And that's not obviously a full description. Range has a little bit funky description in terms of the way it takes its arguments, but all 3 of its arguments are integers, right? Or if I said, what does the sorted function take as an argument? You'd say the sorted function takes a list of elements that are all comparable and can be sorted against each other. So sorted can take a list of strings, but it has to be all strings. It can take a list of numbers, and numbers can be integers and floats. But it has to be all integers and floats, right? Because you can compare integers and floats together in a way where you can sort them. You can compare strings in a way together in a way that you can sort them, but you can't compare like strings and integers, for example. So that's the kind of thing, right? So when you're thinking about a function that you're learning, such as the examples I gave, range, sorted, that are built in, or when you're thinking about a function that you're writing, you're thinking about what are the inputs and outputs in terms of their types. So when you call the function, you are kind of forced to reckon with that, right? So you also have to think of a good name for it, and a name that is descriptive of its output, right? So this function computes and returns a list. So it computes and returns a list of all the divisors of a positive integer. So when I use this function, I want it to be named something that tells me what it does when I'm using it. So now's my opportunity to name it. So since it computes and returns a list of divisors, I'm just going to call it, I'm going to call it divisors list. So that gives me a sense of what it gives me back, right? So I've kind of given myself a semantically meaningful description of its output. And I often, when I'm naming a variable or a function, I will name it something relating to its type, right? So divisors list, or word frequency dictionary, or um, um, count of vowels. And count to me kind of tells me that it's going to be a number, right? So something that kind of explicitly or implicitly tells me what its type is going to be. Okay, so divisors list, since it's going to give me a list of divisors, it's going to give me a list of divisors of a number that I can get divisors of. So that also kind of tells me that I need to give it an integer. So let's do this, for I in range 20. Oops. And we'll go from 0 to 19. And oh, there we go. So let's get into it. So of course now, here's my tests. If I call it, it's going to give me an error. Here's another good reason to call your function before you define it. Let's say I did something like, I mean, this would be a totally different function, but let's say I decided to call my function like CHR, which I wouldn't call this function CHR, but let's just say I decided to call it CHR for whatever reason. So if I call it before I define it, and then I run it, and it runs, that tells me that function already exists, which I don't want it to do, right? I don't want it to already exist and then define a function def CHR, because I'm just going to overwrite this function that already exists. and maybe you didn't know that there was a function called CHR, right? But there is, and you don't want, Python will let you define a function called CHR, and it'll just overwrite the built-in CHR until your function goes out of scope. So that'll give you an opportunity to rename that, right? So that's another reason to call your function before you write it, is to make sure you're not overwriting an existing function. And here's something else. If you don't fully understand, if it doesn't feel natural, I usually don't like to do this, but just take it, if you would, please, at face value. That I find this to be one of the single most profoundly helpful things that I can do to help me solve a problem quickly. And if it doesn't totally make sense, just do it anyways, and it will make sense eventually. So I'd rather you not take it on faith, but if you have to, do it. Okay, so now that I'm sure I'm not overriding a built-in function, I'll write my function head, and I'm going to think about what I want to return, which is going to be a list of divisors. I'm just going to call it list because it tells me that's the list. I'm going to run it, and I get a bunch of numbers with a bunch of empty lists, which is good. So I'll just see these filled out when we're ready. Okay. Now I have this nice scaffold, right, where I have some tests written, and this kind of test or this kind of function, I like to just throw in a for loop and just test a few numbers. I have the head written, I have a return, so I have all of the elements. I have an input, right? I kind of have all of the elements that I need to make working on this easy and to make it complete, right? Like this is complete at this point in that it's like it has something calling it, it has inputs, it has an output. It doesn't do what I want it to do yet, but it's complete, if you will. So from here, I've gotten all the easy things out of the way, which I always recommend doing the easy things first, and then get into the stuff that's more challenging. Okay, so from here, now I can actually start working on the problem. So I know I need to go through every number that could be a divisor of n, starting at 1 up to n. So I could say for I in range. And I know this range needs to be 1 to n. But let's just say I make this mistake here. Let's just say I say for I in range n, because this kind of loop is a kind of loop that you write all the time, and maybe I'm just on autopilot a little bit. So I'm practicing making a mistake, which is something that I also recommend you do. Like you're like, well, what if I made this mistake here? So you made this mistake, but you can come back and you can find out how you would discover you made that mistake and what you do to fix it. Okay, so whenever I write a for loop, what I like to do is print the identifier. Oh, we're using a while loop. I'm sorry. I can't even use a for loop yet. Okay, so we're going to start I at 0, which, again, I need to start I at 1, but we'll start I at 0. We'll pretend I don't know that. And then I'm going to say while I is less than n. Okay, then I'm going to I plus gets 1 and print I. In this case, I actually do want to start I at 0 because I like to increment my I value right here. So in attempting to make a mistake, I actually did the correct thing. If I had started it at 1, given the way I like to write my while loops with my incrementation of my controller, which I is the controller of this while loop, I like to have that right up at the very front of the loop, or the very top of the loop. It does make more sense to start it at I. Okay, so let's just see what I get. 0 obviously gives me 0, 1. So I'm also seeing the output from this I down here in this loop. So why don't I'll indent these so I can see. Okay, so there's 1, 1, 2. That's 2. 1, 2, 3 for 3. 1, 2, 3, 4 for 4. Okay, so that actually tells me that I'm getting all the correct I values, which is good. Cool. So I tried to make a mistake and I succeeded anyways. I'm gonna roll with it. So now I'm gonna say if n mod I equals 0, then I know that I is a divisor of n. I divides evenly into n, and I can say list dot append I. And I think that'll do it. Real quick here. Just gonna do that, res, and we'll do len. I just want to see the length of everything. And res. Okay. Cool. So 0 has 0 divisors. Its length is 0. It's an empty list. 1 has 1 divisor, which is itself. 2 and 3 are prime numbers, so they only have 2 divisors. 3, 4 has 1, 2, and 4. Okay, cool. And then I can just kind of look through here, make sure everything's squared away. And as a trick, I know that prime numbers are only going to have 2 divisors, which is going to be 1 in itself, at least the way that I wrote this. So I can look for all the prime numbers, and they only have 2 divisors. Good. And that's a pretty good signal that this is working. Okay. I'm not going to show the for loop solution because I want to move on to other things. But I will show what happens if we have a global variable. And why don't I do it like this? Let's just do 5. So if I have this global variable, let's do up to 10, right? So I wanted to give this example. So notice I moved my accumulator out of the function. And Python, like I said, Python lets you do this. It's fine with it. It'll just let you do that. But you might think, oh, well, there's times that I could use that, and there isn't. There's no case where you should do this, which is why I wish it would just give you an error and just say, no, don't do that. But it'll probably never have that error, and that's okay too in its way. So notice this list just keeps growing, right? So 1 has a divisor of 1, 2 has a divisor of 1 and 2, but it also just carries the divisor of 1. So notice every list just has all the divisors of the previous number in it. You know what I mean? So it just keeps accumulating more and more and more and more and more and more and more divisors. So this list exists once, and this function doesn't initialize a new list every time it runs, meaning that it just keeps accumulating onto the same list. Okay, cool. So I will just reiterate this. If you're writing code like this that uses a global variable. You just have a global variable and you just use it. It can be very difficult to anticipate what the behavior of your function is going to be. It can be very hard to accurately predict what your code is going to do. It causes pretty severe maintenance issues. So just be careful about that. I worry that the importance of this is like being, like I worry that I'm saying this, it could sound like, oh, here's a little tip, and it's like, this is in terms of importance, this is a 10 out of 10. Like, there's no reason to use a global variable in your function. You can get away with it once, but the second time you call your function, it's gonna do things. So it's an easy mistake to make. It's definitely something that if you're doing it, it'll take some practice to get out of. So like, no worries, but do just be on the lookout for that and start paying attention if you have global variables just in your function. If you're wondering like, but why have global variables, if I can't use them with my function? A function can use variables in two ways. Either it can create them, or it can use the parameters, and your variable can go into your function through as an argument, right? In this case, it wouldn't make sense to just have a list like this, where we just pass like a list equals an empty list for no reason. But that is preferable to just using a global variable. So if you have a global variable and you want it inside your function, consider either creating that variable local to the function or adding another argument, unless your problem statement says not to. But if you're writing your own code, you get to decide how many arguments your functions have. So consider adding another argument and taking that value in as an argument. Okay, cool. Spiel complete. Okay. So I will spare you the overview this time. It's Saturday. You get the day. That's your day off. Is that I won't go through the overview. So I want to recap while loops. I didn't do the like rate 1 to 3. How are you feeling about while loops? Because while loops are super weird and nobody feels good about them. So we're just doing review of this, and then we're gonna skip ahead a little bit. We're gonna go out of order in the material. I want to cover data structures today, and we're gonna probably do data structures today and Monday, and then we'll pick up the strings material on another day. Okay. So I know we just did a while loop problem. Let's do a sort of a quick recap of while loops from the ground up. You just saw one in action. If you're confused about them, if you're struggling with them, we're going to take it slow. Okay, so a while loop. Okay, I said I wouldn't do the overview, but I need to show you where this all fits together. I'll do a partial overview. Data types, abstractions, control flow, and iteration. Okay, so while loops are categorically, they go in the iteration category, right? We've got for loops and we've got while loops. In terms of the way we think about them functioning, they're very similar to an if, but they do not replace in terms of their utility, how we apply them, they don't have anything to do with control flow. They have to do with iteration. Even though mechanically, the way I'm going to describe them is very similar to an if, functionally, how we use them is in terms of iteration, not control flow. Very distinctly not control flow. Okay, so while loops are loops, they're for iterating. So let's look at it and at an if. They're very similar in terms of the way they work to an if. So an if checks a condition and executes a conclusion. The conclusion is executed if the condition is true. If the condition is false, the conclusion is not executed. Simple as that, right? A while loop checks a condition, and if the condition is true, it executes the conclusion. If the condition is false, it does not execute the conclusion. So that description, that part of the description for an if and a while is the same. Let's turn this into a little breakout. Somebody asked me to post the breakout code. Yes, I will do that really quick. So let's turn this into a little breakout. Given that I just gave essentially the same description of these two, what is the difference? And I didn't get to the difference yet. So what's the question on the table is, given that an if and a while both check a condition, and if the condition is true, they execute their conclusion, what's the difference? Why do we consider a while a loop and if for control flow? I'll give you a minute for this. All right, we got a number of answers. Go ahead and keep putting in your answers. I'm gonna read through and talk about each of these answers given. If you still have an answer, keep thinking about it. So first one is while loop needs to have a way to stop. That is true, but that is a true thing about a while loop, but and it is obviously a difference. But it's a what do they call that? We can infer that from the way that while loops work. It's not quite. It sort of comes after the main difference. Is there a straightforward syntax to check if underscore exists function name that would give true or false? This seems like a different question. We'll come back to that. Let's see. An if statement will only run once. That's true. My take, if versus while. If checks the condition once, while checks the condition while some condition is true. Yeah, so, yep, okay. I'll come back to that. If checks the condition and executes the code, while loop, on the other hand, keeps going until made to stop. A while loop will not stop on its own. Yeah, okay. So basically, Seems like people get the gist of this. So, and I'll explain exactly sort of the moment in which whiles continue and ifs don't, right? So to this point, the description that I gave was the same. They both check a condition. If the condition is true, they execute their conclusion. The difference is once an if executes its conclusion, the Python interpreter, it comes and it looks on line 43, the condition is true, it executes the conclusion on line 44, and then it goes on to line 45, line 46, etc. And it just keeps going down. So it executes the conclusion and just keeps moving. Whereas a while, when it executes, it checks the condition, and then it executes the conclusion, and then it comes back up and checks to see if the condition is still true. If the condition is still true, it executes the conclusion again. So it repeats executing the conclusion until the condition is false. That's how a while loop works. So it checks the condition, executes the conclusion, then it goes back to check the condition again. And that's really the only difference. But even though it's mechanically similar to an if, the way we use it is to replace, or we use it for iteration, not for control flow. Okay, let's see. And then in terms of, I wanted to circle back to this question, in terms of is there straightforward syntax to check if some function name exists that would give true or false? So kind of. The way I can think to do that is to just attempt to call the function in a try except block. And if it throws an error, then just catch the error and have an alternative in your except. But that I don't teach try excepts in premium prep. I just wanted to circle back around to this. If you want to go research it yourself or ask me after class or in study hall, I would go over this. But I did want to touch on it. So there is a way that I can think to do that. The reason I don't teach try except is Python's way of doing error handling. Error handling can be very, very powerful. I taught it in a premium prep class about a year ago. I taught it really early on. I was like, hey, check this out. Every time you get an error, you can work with catching the error in Python and handling the error. And what I did was create a cohort of 30 people that wrote code that never threw errors, which was not a good thing. If your code is naturally going to throw an error, your first best option is to write it in a way where it doesn't throw that error. Not say, oh, I'm getting an error, so I'm just going to use try except to just ignore this error. What you're going to end up with is a ton of really unpredictable and strange behavior because Python can't provide limitations to help you solve the problem. Errors are there to help you code well, right? So you want to see them in general. So try except can be useful for the times when you're just like, yeah, Python, I know you're going to throw an error, but genuinely, I don't care and I want to do this other thing. So it is an interesting side topic, and it's a rabbit hole you can dive into carefully on your own, or ask me after class, outside of class, or in study hall, and I will be happy to muse on it. Try except with an E is what I meant. That's what I said. So different languages have slightly different keywords for that. Okay, So let's talk about open-ended problems. So I've talked about, we looked at a problem that uses a while, where we solved it with a while loop, and I said we actually don't need to solve it with a while loop, we can solve it with a for loop. Then I explained the, kind of the mechanical working of a while loop, but I haven't to this point explained why we would need a while loop, why it would actually be useful to us. I did last class, but let's go over that again. So open-ended problems. So there's a class of problems, that category or class of problems that we can classify as open-ended, which just means, it's kind of a loose term that we use to mean a problem needs a while loop, kind of, right? Open-ended means we don't know at the time that we're writing the code. It's a little reductive to say we don't know, because there's a lot of times where we don't know, like the length of a list when we're writing the code, but we use a for loop because a for loop will determine the length of the list naturally, right? So it's not that we don't know, it's that we can't determine how many times we need to iterate through a process. What does reductive mean in terms of open-ended problems? I was saying, I was using that term not to refer to open-ended problems. I was using it to refer to how I stated that before. So yeah, if that was confusing, just ignore it. So let's see. If you encounter a problem where you can't determine the number of iterations necessary to solve it at the time that you're writing the code, you can't write code that will determine the number of times to solve it, or the number of the number of iterations needed to solve the problem, then you need to write a while loop. And I gave an example of that. We did like an is prime and then next prime example. So yeah, so shoot, I think I'll just give that example again. So let's do is prime. And I'm going to code these out. I'm going to do it quickly. I suggest you code along with me. I'm going to write my test first. So is prime, we can write with a for loop. If n is less than 2, return number is not prime. For I in range, we'll go to 2 to the square root of n, which is going to be n to the power of 1 over 2. And we're going to make that into an integer. And we also want to include the square root, which is just going to be plus 1. And for I in range, okay, then we say if n over I has a remainder of 0, n mod I equals 0, then return false. If we make it through the whole loop without returning false and stopping the function, therefore stopping the loop, then we can return true. Okay, so there's our is prime function. So all I needed to do was check every number between 2 and the square root of n, including the square root of n. And if any of those numbers divides evenly into I, then I'll return false. Just clean it up a little bit. Now let's use the, now let's write the next prime. Def next prime, we'll take in, and it'll return the next prime number, right? So I'm just going to use the same tests, and I'm going to use the, oops, prime, I'm going to use the isPrime function inside. So I don't know how many numbers I need to check, right? So if I call next prime, and let's take this out of the for loop for now, just so we can look at specific scenarios. If I call, why don't I just pick a number, 342. How many numbers do I need to check before I find the next prime number? If I knew that, then I mean, primes wouldn't be that interesting. I mean, kind of the interesting thing about primes is we don't know how to predict them without brute force, right? This is a brute force solution. This is really the only way we know how to get primes, right? Like, we can make this, there are other optimizations that I could do to this. I wanted to keep it relatively simple just so we can, you know, move along, but there are more efficient ways of doing this. But at the end of the day, checking for primes is this. You just have to check every number, and if you find a number, if you find a factor, then you know that number is not prime. So so this is a brute force solution. So that's the thing. Like, I don't know how many numbers I need to check, and I can't write code to determine it without just writing this, like, the code to determine how many numbers I need to check to get to the next prime number is the code to just find the next prime number. You know what I mean? So given that that's the case, I need a looping system that will just keep going until it finds a prime number. So when I'm thinking through problems, I have an internal dialogue. A lot of times it's an external dialogue. A lot of times I literally will talk the problem out. And I recommend that you all try this if you don't do it already. It's called rubber duckying, like where you explain the problem to a rubber ducky or something. A lot of programmers will have a rubber ducky on their desk, and it's kind of an homage to that idea. It's kind of a meme, like a little industry joke, but so it can be helpful to like describe a problem. So when I'm doing that, there are like keywords that I look out for. So if I say I need to keep checking numbers until is kind of a keyword that if I'm describing a problem and I say I need to do something until this happens, until is kind of a synonym for a while loop, right? I need to keep going while I don't have a prime number. If the number I am looking at isn't prime, I just need to check the next one forever until I find a prime number. So if I say until in describing the problem, if I think that word until, then I know I probably got to use a while loop. So I'll say while not is prime n. So remember, not inverts a Boolean, is prime tells me whether n is prime or not. While executes its conclusion when its condition is true. So if the number is not prime, it gives me false. And I wanted to actually continue looping when is prime gives me back false, not true, right? So what I want to do is check the inverse of this. So to say I want this while's condition to be true when is prime would give me false. And then I want the condition to be false when the number is prime. So I want it to be false when is prime would give me true. So I just want it to be the opposite of that. So I throw a not in front of it. And it's a little bit like clunky kind of pigeon English, right? Like while not is prime in, it's kind of like saying while in is not prime, but we're constrained a little bit because Python. So while not is prime in, then we'll in plus gets 1, and I like to actually check n plus 1 here. I want to check the next number because let's say if I give it a prime number, I don't want it to return the number I gave it. I want it to check the next number. So I'll have it check the next number, and that just means I have to return, when I return, I have to return n plus 1 because that was the number that I checked and determined was prime. Okay, cool. So 347. So I didn't need to go that far. I just needed to check 5 numbers. But I had no way of knowing that until I just did it. So this is a case where you have to use a while loop. This prior problem is a case where you don't have to use a while loop. And you know, like if you were actually writing this code, you should use a for loop because for loops are easier to deal with and while loops are weird. Okay, cool. Would it be wrong to use else return true at the end of this? At the end of next prime or is prime? Is prime. Would I use it in the loop or outside the loop? This is in the loop. I presume what you're saying is to use it here as an alternative to this to this if here. This is what I'm guessing you're saying. Is that right? Okay. So this won't work. I'll tell you why, but let me see. Does somebody want to? I'll give you. We'll turn this into a little breakout. Who can tell me why this won't work? Real quick. Thumbs up in chat if you know why this won't work. Okay. Only a few. Okay. All right. Okay. Does one of y'all want to explain it? Thumbs up if you want to explain it. Thumbs down for those of you who said thumbs up. Thumbs down if you don't want to explain it. Doesn't go through the whole loop. Yep. While not check full loop. Yeah. Yep. Once you return true, you won't finish the entire loop. Yeah. So we'll not have gone through all the, yeah, okay. So, cool. There's a few good descriptions in here. And I wanted to just put it to you all to like kind of make you look at this and think about it. So, when you have an if followed by any number between 0 and n elifs, right? I could have an if with any number of elifs here. In this case, we have 0. Ending with an else, what you're saying is you've chained those conditions together. Okay, so these else has to come directly after and horizontally in line with an if or an elif, right? I can't just have an else, obviously, like this, right? So it's necessarily part of a chain of conditions. When we chain together conditions with if, elif, and else, what we're doing is saying only one of these conclusions will be reached. Only one, right? So if I have if and then 8 elifs and then an else, what I'm saying is only one of those only one of their conclusions will be reached. As soon as it finds a true condition, it executes the conclusion and it doesn't even check any of the ones below. An else is a catch-all to all prior conditions. In this case, there's just one. So when a chain of conditions ends in an else, I can say not only will only one be executed, but one of them definitely will be executed. What you're saying is if you don't run this, then you have to run this. So in the example that I gave before, if 8 elifs and then an else, if the if and then the 8 elifs were all, their conditions were all false, then the else is guaranteed to be executed. So if you have a chain of conditions that ends in an else, you are guaranteeing one of the conclusions will be run. If none of the other ifs or elifs are run, the else will be run. So since this is a return, it terminates the whole function. So what this is like saying is if I have an elif here, I can simplify this code to n mod 2 because that's the only number that would be checked, and then this functions as an is even function, not an is or I guess it actually functions as an is odd function, not an is prime. So I wanted to dig into this, and to the person asking this, I know I'm being kind of vehement with my answer. I don't mean to put you on the spot at all. This is a good question, to be clear. It's a good question. I'm glad you asked this because I get this a lot, and that's why I wanted to kind of dig into this a little bit, because it can be tempting. I see this a lot, and I remember going through this when I was first learning. It can be tempting to say, to like want to have like an easy rule of thumb, like all of my ifs should have an else after them. And it definitely kind of makes the whole thing feel complete. However, it, like this system as an if else is logically different from a solo if, right? Like it is functionally different logic. It functions in a distinct way, right? And that doesn't mean one is better than the other. It just means here's a tool for this set of jobs and here's a tool for this set of jobs. They're distinct patterns. So I see this a lot and I wanted to address it because it's an important thing, and I'm sure you're not the only person wondering this. So thanks for asking, and hopefully, I don't know, let me know if that makes it clear. I think that it's probably clear at this point, but I forget who asked that. Okay. Awesome, cool. Just to be very clear, thanks for asking that. That was a good question. I realized like midway through there, I'm like, oh, I hope I'm not like hope you don't feel like I'm like roasting you for asking this question or anything. Okay. Okay, good. And it looks like we're caught up. I want to pivot. I want to pivot away from while loops. I mean, I love while loops. They're terrible. They're powerful. They're a lot of fun. But I want to get into data structures. We are so short on time. Happens every single class. Will I explain why I add 1 to the square root of n? Some numbers have 9. 9 would be a prime number, except the only number that it's divisible by is its square root, which is 3. So you have to include the square root, right? If I didn't include the square root, 9 would be considered a prime number. Does that make sense? Because 9's divisors are 1, 9. It's not divisible by 2. Its square root is 3, and it's divisible by 3, and that's it. And there won't be, the minimum limit of numbers that you can check is starting at 2 up to and including the square root of a number. There are other optimizations that you can make in that too, but anyways, okay. Let's reconvene at 20 minutes after the hour. Let's take a short break. Apologies for the shortness of the break, but we've got a lot to get through. All right, and we're back. Get my screen share up and running, and we'll go from there. Cool. I will paste the code. I don't want to blow up the thread too much with code with the whole document, but I will paste it at the end. I'll paste the whole document. Okay. Let's have a last call. I just want to put a minute on the clock. If you have questions about while loops, go ahead and put those in. We'll go over these breakouts next time. I want to pivot to dictionaries, sets, and tuples. Okay, no questions on while loops. Data structures. So we've got dictionaries, sets, tuples. So in terms of our overview, these are data types. Int, float, bool, string, none. We've covered lists. So these are all the ones that we've covered so far. Tuples go here. And I'll just put an exclamation before all the ones that we're going to cover. Dict, and I'm using the Python descriptors for these. Okay, so we're going to cover tuples, dictionaries, and sets. Actually, dictionaries, then sets, then tuples. So I want to mention tuples first really quickly, and then we'll kind of explore those last, probably in the next class. So tuples are like lists. They don't have mutable methods, and that's the difference. So any mutable operation that you can apply to a list can't be applied to a tuple, and that's it. Let me illustrate that for just a second, and then we're going to get into dictionaries right away. Print dir list. Let's do the same thing for tuple. Oops. Okay. Oh, come on. Okay, fine. Fine. We'll do it your way. Okay, so here's the directories for both. Remember, you can ignore the non-regular named methods, right? So the ones that are important for us are these ones for lists, and for tuples, just these two. So tuples only have the two methods. Notice these are methods from lists, actually. You know how these work if you know how they work in lists. They work exactly the same. These are the two methods for lists that return a value rather than cause a mutation, right? All of the other ones cause a mutation in lists. The only exception to that is copy, but the only reason copy needs to exist is because we might mutate the list and we want to mutate a copy or mutate the original and save a copy or something, right? So copy doesn't directly cause a mutation, but the only reason that it's useful is because lists are mutable. So append changes the list by adding an element into it. Clear changes the list by removing all the elements in the list. Copy exists because, like I said, since we can change things about a list, we might want to like preserve certain states of the list before we make the changes. So it doesn't cause a mutation, but it's only useful in the context of mutability. Count is immutable. Extend is like append, but for multiple elements. It adds elements to the end of the list. Index, like count, doesn't cause a change. It's immutable. Returns a value. Insert is like append and extend in that it adds a value to the list, except instead of adding it at the end, you can specify the index in which to put the value. Pop removes a value at an index that you pass. If you don't pass any index, then it removes the last value and it returns it. So pop is the weird one in that it both removes a value from the list and returns it. So it does two things. It's the only method that I know of that does both a return and, or at least for the built-in types, it has a return and a mutation. Remove obviously removes an element. Reverses the list. Sorts the list. So both of these are in place operations. So if I went through, if I was thinking, oh, it sure would be nice to have an immutable list, let me just get rid of all the things that cause a mutation in the list, and then we'll just do that. Then I end up with a tuple. So that's what a tuple is. We'll talk about like how to use those a little more. There's some implications of that, but I just want to kind of prime you. Tuples sound like they're going to be this kind of strange thing, but they're just immutable lists. We'll talk about how to use those later. Dictionaries. So dictionaries are, I'm just going to say it, I think the most complicated of the built-in types. They have, I guess I could say, the most moving parts. There's a little to them. They're not terribly complicated, but there's often a bit of a learning curve. I don't expect by the end of this that all or even most of you are going to be comfortable with working with dictionaries in the same way that you were when we first introduced lists, because lists are like, hey, you have objects and then you can have a list of them. Okay, well, here's a data type that's just a group of things, right? And then I show you the indices and it's like, okay, so I add things in and then they get an index. Great. So dictionaries, one way of understanding dictionaries is that you can think about them as similar to lists, except let's do this, sorry. They are similar to lists, except that they, instead of having indices, they have keys. And we'll talk about the difference between an index and a key. So with a list, I have an empty list. This is something that I think you all are at least familiar with, if not comfortable with. I have a list, empty list, and I can print the list, I can alter the list. Easy. We use the append method. Most of the time we're causing an alteration in the list, we're using an append method, which just adds an element to the list, to the right-hand side of the list. Elements are preserved in the order that they're added. I can use insert to add an element at a specific place. I can use pop to remove an element. I could use pop and insert together to rearrange items, right? I could pop an item off, which removes it and returns it. And then I could use insert to figure out where, I could use some process to figure out where I should put this element that I popped, and use insert to put it there, right? So we're not getting into like sorting algorithms, but if we wanted to do an in-place sort, if you look up at in-place sorting algorithms, you could use pop and insert to like move things around in a list, right? And that can be pretty handy. There's also other ways of doing swaps, swapping elements in a list. So it's pretty straightforward, and it's important to know that one, the elements are preserved in the order that they're made to be in. And it's important to know also that that order is not a given. It's a designed feature of lists, right? Like since we as humans, we tend to be good at like spatial reasoning, thinking of things as objects in space in order makes sense, right? But it's not a given for a data type in a programming language. It's a feature that has to be designed. Dictionaries do not regard the order of their elements as meaningful in the same way that lists do. So as of more recently, it used to be the case a year ago that, and I would demonstrate this. This was really easy to demonstrate a year ago. I would make a dictionary and I would print it out a few times, and the elements would come out in different orders. That doesn't happen anymore. Dictionaries will retain their order, but you don't actually have control over that order. And it's because we still don't think about dictionaries as an ordered type. And it's important that when you're thinking about a dictionary, you're not thinking, here's the first element and here's the next element, right? The analogy that I like to use is if I gave you a jar of jelly beans and I said, or a bowl, right? And I said, hand me the first jelly bean in this bowl. What does that even mean? Where do I start? Do you start from the perimeter? Do you like calculate the jelly bean on the surface that is most in the center? Or do you start from the bottom? Like, there is no first jelly bean in a bowl of jelly beans, right? They're just all in there together, right? So if I said, hand me the 15th jelly bean, that's even more complicated, because if you can't determine a first, how the heck do you determine a second and a third? It just like if you had a schema to do one, the order of complexity for doing anything else would just go up tremendously. So having items in a list is like having, if I handed you like, I don't know, if I arranged items on a shelf from left to right, and I could add items onto the shelf and remove items from the shelf and swap the position of items, right? If there were items on a shelf and I said, hand me the third item on that shelf, you'd probably start from the left and you'd go 1, 2, 3. You'd use a 1 based index and you go 1, 2, 3, and you'd pick that item, right? So that's how lists are arranged. That's not how dictionaries are arranged. Okay, so let's actually look at a dictionary. So I've got a dictionary, D. So dictionaries don't have indices. Instead of having indices that are just given automatically, right? Whenever I add an element into a list, it automatically gets an index. Whenever I add something to a dictionary, I have to add a key, which is the analog for an index, and a value together. So when I add something to a list, it's just one element. I'm just adding one thing, and it automatically gets an index. When I add something to a dictionary, I have to explicitly state, or I have to determine in my code what the key should be, and then add that key and value together explicitly. So we can, just like I could have a list with elements in it, right? Let's do this. 44, 55, 77. Why not? So we've got a list with elements in it. Let's have a dictionary. Let's add some things to it. So these are at index 0, 1, and 2. So I have to explicitly give keys for these elements. So to make a dictionary with a key value pair, I'm going to call the keys A, B, and C. So for each key, I'm going to pair it with a value. So I'm going to say A, and let's do 44 at A. Let's do colon 55 at B, and colon 77. Now, I don't particularly like having multiple elements in a dictionary on one line like this. I think it looks a little funky. What I like to do is format my dictionaries, breaking things onto other lines, and putting one key value pair per line. That looks a little better. So with this, I have keys on the left. You always have your keys on the left, separated from their values on the right by a colon. That's the syntax to declare an empty dictionary. Or excuse me, not an empty dictionary, but a dictionary with a non-empty dictionary. Okay, cool. So let's do print D. Okay, so with a list, if I wanted to print off, say, this 55 here, how would I do that with a list? I'll put this in Slack. We'll break out. Go ahead and copy paste my code and show me how I would alter the second line in what I just pasted in Slack, which is this line. Show me how I would alter that line so that that print would print out the 55. And you don't want to just do 55 like that. That's cheating. You want to get it from the list. Okay, go ahead and get in your answers. We don't even need a minute for this one. I just want to make sure you all know how to do this. Well, I mean, I want to make you do it, and then show you that it's kind of the same for dictionaries. And this is kind of this kind of tends to be true with dictionaries, is it's the same as with lists, but it doesn't feel the same. So they're kind of strange that way. Cool. Okay, so indeed, if I want to print 55, I just find the index of 55. Okay, so 5501, it's at index 1, and I just say list, and I subscript into index 1 by saying list brackets 1, list sub 1. That's how I would read that, and then we're good to go. Okay, so given that, given that you know, I'm going to presume that most or all of you know how to do this, or if you didn't, that you can at least look at everybody else's code and see the trend that, or listen, or look at this code and see that, you know, I've just picked the index of 55. That'll get me that element 55, right? So given that you know how to get an element and an index, and given that I'm telling you that these are the keys in the dictionary right here, and how would I, and I'm telling you that keys are in dictionaries the analog to indices and lists. That is, keys are to dictionaries as indices are to lists. How would I get this dictionary to also print 55? You beat me to it. Go ahead and take a guess, if you must. So the keys are the same as the indices. It's just the indices are automatically given in a list, whereas in a dictionary, I have to explicitly state them. Okay, cool. Yeah, so same deal, square brackets. A lot of people think, oh, well, since you declare a list with square brackets and you declare a dictionary with curly brackets, then a lot of people will think, oh, maybe you use curly brackets, and you don't. You do still use square brackets. So you'll print D sub key name. In this case, the key of 55 is B. Now I always have somebody ask me like, okay, well, how do I this, you know, I can get the value if I know the key, but if I have the key, how do I get the value? And you can't do that. It's just as simple as that. It just doesn't work that way. Just like if in a list you have the value, you can't use that to get the index. You can use the index method, but it's a little limited. If I have 55 in this list and I do list.index 55, it's only going to give me the first index. You know, it doesn't really give me an index, a picture of like where all the indices are. So essentially, if I know 55 and I want to know what the key of 55 is, I could write a function that would do that. I can iterate through a dictionary and just find if the value is 55, you know, capture the key and stop iterating. But there's no mechanism built in to do that. Somebody's asking, does that mean if you have a long list of values in a dictionary, you must know the index key? So I'm going to be particular about this. So there, when you say index key, you are correct to analogize index to key, but I want you to know, you can call it an index key for now if you want, but I want you to know that there is no index. These elements have no numbered value associated with their order. So to be clear, if you have a long list of values in a dictionary, you must know the keys, or yes, so you have to know the keys in order to extract the value. But if you have the dictionary, you have the keys, you know. So I'll show you how to work with them. It's not terribly bad. You don't have to know them in the sense of like keep them in your head and have them memorized. There are ways of like getting Python to say, okay, here's an arbitrary dictionary, and here's the keys and here's the values, and you can just kind of start playing with it. So cool. All right. So let's look at iterating. Iteration. Yeah, okay. So if I iterate through a list, I should do something like this too. Let's do D, and we'll make D 55 as well. So if I iterate through a list, for element in list, print element. Iterating through a list, I mean, this is how I taught iteration. I mean, I literally taught you lists first, and then I taught you how to use a for loop. So it's pretty natural, right? Like Python makes this really easy. And it's not terribly difficult with a dictionary, but there's something that you have to remember to do. So just real quick, I'll just run the list code. There you go. So when you iterate through a dictionary, well, here I'll use a list example again. You may recall the enumerate function. You may recall enumerate. Okay, so for IDX, an element in enumerate, we can enumerate the list, and remember how enumerate gives us the opportunity to change our for loop a little bit. So it can change our for loop a little bit. We can when we iterate through a dictionary, since this is iterating through the indices and the elements of a list, in a list we call them indices and elements, in a dictionary we call them keys and values. So since this lets us iterate through the indices and elements of a list, a dictionary has keys and values, which are the keys are analogous to an index and the values are analogous to an element. So we iterate through a dictionary. When we iterate through a dictionary, it looks a little more like this in that we have to have both things. It's very advantageous to have both. So you want to say for, and convention here is K, V, N, or I mean, there's multiple convention. You could say key, val, whatever. And then you'll do your dictionary name, which in this case is D dot items, ITEMS, items. Okay, items is a method, takes parentheses after it, we want to invoke it. Now let's print key and val, IDX and element. Okay. Oops. there we go. So here's our list. Here's our dictionary. So when you iterate through a dictionary, there are other things that you can do other than items. This is another one of those things where Python will let you do this. You can iterate through just the dictionary, but if you do that, you're only going to get the key. You will only get the key. So if you're expecting this to give you keys and values, unfortunately, it won't do that. When you iterate through a dictionary, don't think, do I need to iterate through the keys? Do I need to iterate through the values? Do I need to iterate through both? Just make the assumption that you need to iterate through both for now, right? Like you can worry about optimization issues later. It's not that unoptimal to just iterate through both anyways. If you're doing it at all, you're might as well just do both, and that gives you more options in your loop. So you can do for key val in d.items, and just like with everything where in a loop, you know, I don't have to call these key and val. I could call these foo and bar. I could call these sandwich and potato. But those aren't good names for what we're doing. Key and val are just you know, descriptive in this case, so I'm using key and val. Okay. K and V are also acceptable in this case, but K and V can also mean different things in other contexts. So key and val. Okay, so we talked about declaring dictionary with elements, list with elements, finding a value in a dictionary is like finding a value in a list. Iterating, just remember to use the .items method, excuse me. Just remember to use the .items method when you're iterating through a dictionary. One thing that's really common to do with lists is to append, right? We want to add elements to list. You see me, you probably do this all the time, right? We want to .append. And the way I like to add things into a dictionary is a little different here. It looks a little different. So when I add something to a dictionary, I have to add a key and a value. I can't just add a key without a value. You can't have an orphaned key or an orphaned value. Just like in a list, you can't have two of the same index. Like, what would that even mean? What would it mean to have two index 3s? I mean, you could have two elements at index 3 if they were in another list or in a tuple, but you don't really have two elements at that index. You just have one element that contains two elements, right? So either in any case, you only have one index of each number, starting from 0 up to however long the list is minus 1. Same thing with a dictionary. You can't have multiple of the same keys. So I can't have two index, let's try to do this, index A's, like that. So if I try to make two of the same index, it's going to overwrite the previous one with the last one given, which is, that can be useful if I want to change something, but we'll look at that in a second. So there's how I can add to a list. So let's talk about adding an element to a dictionary. So when you're adding an element to a list, you just say, just add this element, and it gets an index automatically. Nice and easy. Okay, when I add an element to a dictionary, I have to supply the key and the element that I want to add, or the value that I want to add. So I have to say D. Now this is similar to accessing the element, right? So D sub B, so I've got A, B, C, D. So I'll say, let's add the key E. I'll say D sub E equals hello. And let's do it before and after of the dictionary. We're not doing anything for lists. Whoops. Oops. I'm like, why is nothing printing? Okay, so dictionary. So you can see here's my before I add the element, here's my after. So this looks different than an append, but this is how I recommend doing your append. This is the analog to add a key value pair into a dictionary, just like append adds an index element pair into a list. Okay. So we covered creating, reading, updating. Let's talk about deleting. So anytime I'm learning a new collection type, I forgot to mention this. Anytime I'm learning a new collection type, there can be more to it than this, but I try to do CRUD, R-U-D. How do I create the type? How do I read from it? How do I update it? And how do I delete it, right? This can also be applied to how do I create new elements inside the type? How do I read elements, which is kind of the same thing? How do I update a given element? And how do I delete a given element, right? So it can be applied to the whole thing or just one element at a time, right? So kind of know those for lists. And let's just look at deleting from a dictionary really quick. If I want to delete, let's say I want to delete C77 here, I can say del. So del doesn't have any special bearing on dictionaries. This is actually a keyword like def and for and if and while. It's a keyword that just is for deleting things. I can delete anything with del. I can delete the whole dictionary actually. If I wanted to delete the whole dictionary, this would work for the list too. So notice that I get this D is not defined error, right? So this is going to work fine, but if I try to access D after the del, it's like that name doesn't even exist. Python has no idea what I mean. The whole dictionary is gone. And this would work exactly the same for lists. If I want to delete an index, or excuse me, a key from a dictionary, I can say del d sub key name, and then notice here's my dictionary before, and here's after, and I'm missing the key value pair where that key was. I can also use pop. I kind of prefer to use del, but I could say d.pop. And this does something really similar. Oops. We have to give it a key, C. So you can use either one of these. Doesn't really matter. I mean, like I said, I kind of prefer del, but I don't know. Why do I prefer del? I use del, and I'm like looking at this, and I'm like, but pop, like in lists, returns the value. I'm going to start using pop now. Okay. Just like in lists, I just looked at this, and I'm like, why do I prefer del? Yeah, you should use pop. Seems better. I'm not sure why I don't do that. Okay. So if you want to remove something, you can use del or pop. Pop returns the element before it deletes it. So if you want to capture that element, you can do it that way. Okay, cool. All right, and that actually puts us right at time. So we covered create, read, update, delete with dictionaries, which is exactly where I wanted to get to. Cool. Next Monday, we're going to dig into more dictionary stuff. We're going to dig into it pretty hard. We're going to start with that, review this, and just do some dictionary problems. And then on on Monday I'll try to get through sets and tuples in the latter half of class. I'll try to get through those together. Cool. If you're done for the day, then have a good rest of your day. Class is officially over. Thanks for hanging out. Let me stop the recordings and we will open up for questions.